Standard form officially is ax plus by equals c. Now, do you absolutely need to know it? Not technically. Um, you can get pretty far with y equals mx plus b, but when they ask about slope, which will do a bunch of problems, it's a huge shortcut. So that would be something like 3x plus 6y equals 13 or something. That would be standard form. And the slope in standard form is negative a over b. Now, that negative can be hard to remember, so hopefully it helps a bit if you think, well, if we wanted to turn this into y equals mx plus b, we'd have to get y by itself. So we would do minus 3x to both sides, minus 3x to both sides. So that's why it ends up being negative, right? And then we would have to divide by 6 to both sides to get y equals, so that's why it's dividing. So at any rate, but you don't actually have to do that because of the shortcut. So if somebody says, oh, what is the slope here? It's literally negative a, so your a is 3, divided by b, which is 6. So negative 3 over 6, or negative 1/2, done, that's your slope. So it's a really nice shortcut. If we do another, it would be, let's say we have something like, I don't know, 15x minus 10y equals 10. Okay, negative a is negative 15 over b is negative 10. So negative 15 over negative 10, which I guess would be, what, 15 over 10, which if we divide by 5 would be, what, 3 over 2? Yeah, like 1/2. So that is the first equation, and we'll do some problems with that later. If two straight lines have no solution, they're parallel, they have the same slope. So if you're in a linear system and there's no solution, you know you are looking for same slope. Infinite solutions is less common on the SAT, but infinite solutions would mean the lines never stop intersecting. They're the same line. So that means same slope, also same y-intercept. It's a lot less common. Typically, you're going to be looking for parallel lines. All right, now we're into some of the good stuff. So quadratics, these are your ax squared plus bx plus c. Now, the x-coordinate of the vertex, this is really important. It comes up a lot, and that's going to be negative b over 2a. Now, a lot of people know this already. You might know that it comes from the quadratic formula, right? Remember in the quadratic formula, you've got your negative b plus or minus the square root of some stuff divided by 2a. So that's where this comes from. Your vertex is going to be at negative b over 2a. So let's say you've got an equation that's like, I don't know, 5x squared plus 20x plus 2. Just pulling random numbers here. Negative b, well, this is our b value. This is our a, b, and c. So negative b is negative 20. Divided by 2a is divided by 2 times 5. 2 times 5, okay, that's just 10. So this is negative 20 over 10, which of course is, we can cut the zeros, negative 2. So if somebody says, hey, what is the x-coordinate of the vertex for this equation? You can just do it in your head. Negative 20 over 10, done. Negative 2. Of course, on the SAT or the digital ACT, you can just throw this into Desmos and look at the graph as well, but it's faster to just do it in your head. Now, the y-coordinate of the vertex, you don't have any fancy equations. At least I don't know any for it. What we would have to do if we wanted to find the y-coordinate of the vertex is we'd have to plug in that negative 2 for x and then solve. So 5 times negative 2 squared, 20 times negative 2 plus 2, and that takes a while. Realistically, I would just throw it into Desmos. All right, so that's your negative b over 2a. Now, the sum of solutions comes up less often, but still sometimes. I would say the x-coordinate of the vertex, like you need that a lot. The sum of solutions, it's actually something I didn't know until I watched my favorite YouTube channel, Tutorlini, which if you're my student, you're very familiar with it. Well, it's not my favorite YouTube channel, it's my favorite SAT YouTube channel. So sum of solutions is kind of interesting. It's very similar to the x-coordinate of the vertex. It's negative b divided by 1a. And the reason why that works is because let's imagine we've got some graph and we've got two solutions here, and then we've got our vertex there. Well, the vertex is exactly the midpoint between these. It's exactly the axis of symmetry. So If we average these, right, if we average them, we add them up and divide by 2, then we end up at the vertex, at least in terms of the x coordinate. So we sum them and divide by 2 to get this. So if we just sum them, we just sum them. Sometimes it's useful, especially if the question says, hey, what is the sum of solutions? It helps. So let's say we have, 6x squared plus 7x minus 5 or something. Our sum of solutions is literally just negative b, negative 7 over a 6. If we wanted our x coordinate of the vertex, it would be negative b over 2a, so negative 7 over 6 times 2, which is negative 7 over 12. All right, the product of solutions isn't as common, but if you were to multiply the solutions together, you would get c over a. You can derive this from the quadratic formula if you'd like. It's kind of cool, but I don't. It's not really necessary just for the test. Now, this stuff is different, and this is where we're starting to get into solving tricky questions, dealing with differences, completing the squared, et cetera, et cetera. So if you FOIL these out, which we don't have time to do today, so I'm not going to, but if you FOIL these out, you'll see that x plus a times x minus a is x squared minus a squared. The reason why it works is because when you FOIL it out, or if you use the box method, the plus ax and minus ax cancel out. So, you think it's x squared plus ax minus ax. Wait a minute, that cancels. It leaves you with x squared minus a squared. So, for example, if we find that we have x squared minus 16, we know that's really, oh, well, our a squared is 16, so our a is 4. So this is x plus 4 times x minus 4. And we'll see how this might appear in problems. It's really useful to identify. Yeah, makes life a lot easier. With this is if you want to do a difference of squares, which you may have to for circle questions. Again, you could FOIL it out. You'll find that it's x squared plus ax plus another ax. So it ends up being plus 2ax plus a squared. These are all a's, they're not nines. So again, that 2ax is because it's plus ax, but then plus another ax, because it's just the same thing squared. So for example, if we have x squared plus 10x plus 25, we know that that is just x plus 5 squared, because 2 times a is 10, so our a is 5, and then 5 squared is 25. And with completing the square, that also lets us do things with like this. If we have like x squared plus 18x, and maybe we don't have plus anything, or we have just like, I don't know, plus c or something. We can say, okay, well, I don't need to worry about this guy because I know that 2 times a gives us this. So 2 times what gives us 18? Divide by 2, it's 9. So x plus 9 squared would give us this, only we have that c. So we could say, oh, well, this is just like x plus 9 squared, only we have a c instead of an 81. So maybe it's minus 81 and then plus c or something like that. We're not going to get into too much detail right now. A lot of people like to do it this way, where they just keep it with their thing, and then they put the 81 on the other side. If you're totally new to completing the square, I would say check Khan Academy. But what I just want to communicate with this is that sometimes this is like, oh yeah, obviously this is x plus 5, that's nice, but that isn't always reliable. The number with the x is always reliable. We say, okay, divide it by 2, and then we'll get our number. Okay, and then finally, vertex form. I'd say this is very, very important. Again, anything about vertices, the vertex is very, very important. So vertex form, this is a times x minus h squared plus k. And what are all these numbers? Well, hk represents the vertex, so that's the x and the y of the vertex. And then a is it's sort of like the slope. It's like the gradient. If a is positive, then it tells you that your graph is smiling up. Imagine like a little smiley face. If a is a negative number, your graph is frowning. So keep that in mind. If a is positive, it's a smile. If a is negative, it's a brown. And this is just really useful if they give you the vertex, right? If they say, oh, the vertex is at 3, 2, and it also has a point at 10, 11 or something. What is the equation? You can then plug in the vertex. So yeah, that's vertex form. One thing to note is notice the kind of standard form here has almost no constants in common. The only one we have in common here is A. So that's useful if you need to convert between these. If they say like, oh, what is C according to this? Well, I don't know, because C is not necessarily the same as K. It's probably not the same. But A is the same. So if we know that A here is 4 and that these are equivalent expressions, equivalent equations, then this A is also 4. All right, so the discriminant, this comes from the quadratic formula. This is your b squared minus 4ac. It tells us the number of solutions, right? Number of zeros, number of x-intercepts for a quadratic. So always keep in mind, if you have a question that asks for the number of solutions to something or asks you about solutions, take a moment and think, wait, is it asking for solutions for a quadratic, like a parabola, or is it asking for solutions for a system of linear equations? Because you're going to solve it in very different ways. So remember that in your quadratic formula, b squared minus 4ac is under the square root. And on the SAT, they only have real numbers. It's a little different on the ACT, but so they would consider there's no real solutions if you try to square root a negative, right? What is the square root of like negative 16? Well, there's no real number that you can multiply times itself and get a negative. That's just not doable. So if b squared minus 4ac is a negative number, then there's just no solutions. There's no real solutions because we can't square root it. So typically there's two solutions because you know in your quadratic formula you're doing plus this and also minus this. So if b squared minus 4ac is just a positive number, there's two solutions. And that's pretty normal, right? If we do plus 5 but then also minus 5, we end up with two totally different answers. So b squared minus 4ac is greater than 0 has two solutions. If it is less than 0, so if it's a negative number, there's no solutions, right? Remember, because it's under the square root, we can't square root a negative and get a real number. It's not often that there will be only one solution, but there is one number that if we do plus and we do minus, it doesn't make a difference. And that number is 0, right? If b squared minus 4ac is equal to 0, then we're doing plus 0, but we're also doing minus 0, neither of which makes a difference. So if it's equal to 0, if your discriminant is equal to 0, there is one solution. Now the solution isn't necessarily 0. Remember, this isn't the whole quadratic formula. It just tells you how many solutions there are. So be careful with that. It doesn't mean that the solution is 0. It just means if b squared minus 4ac is 0, there's one solution somewhere. And you could use the quadratic formula to find it, or you could just use Desmos. So that's actually something that we're not going to talk too much about today. I do have a free course on this on Desmos, but I don't use the discriminant a ton unless it's a hard problem that has a lot of constants. For example, if it just gives me an equation, even if it is a pretty scary looking equation, like negative 612 x squared plus 32 over 7x minus 16 pi over 5. I don't know. I'm just like making the worst equation of all time. If it asks how many solutions does this have, I'm just going to literally type this entire thing into Desmos and look at the graph and be like, oh, that's how many solutions it has. Great, done. I'm not going to use the discriminant. But if we had something where rather than actual numbers here, we had like c over x and negative aq x squared or something weird like that where you can't just plug the numbers into Desmos, then we probably are going to have to do stuff with that.